Okay, so you all look a little, I guess you have some consternation because of the midterms that I just walked in with. Yeah, you can collect it after class if you are around. And if not, you can come to my office and get it. So I don't know if you saw the so quick note on that. I was hoping that you guys would have done much better than typical. I don't know if it's true that it's much. I haven't been able to sort of sift through the data, but just eyeballing it, the graph that I saw looked a little better. Let's put it this way, I haven't been able to measure the statistical significance of the difference, but certainly your mean is about 1.5 higher than last year's, and your standard deviation is smaller, which means that at least you are not, in other words, last year, the spread would have been bigger, and you'd have had more people getting more disparate grades. So now your grades are a little more clustered towards that mean, which is better as a group. But we still have to actually do the statistics to check how good that actually is. But anyway, I'm encouraged a little bit. And by the way, I haven't even factored out the zeros. Like for all the people who didn't show up, all those zeros are still in there. So your mean is actually probably going to be a little bit better by the time we're finished. Sorry? Sorry, what? You think I should average them in there? I didn't hear what you were saying. Oh, well, people don't show up. So if you don't have 50, sorry? Nobody did it and got 0. Why, you're worried they're in that boat? Nobody did it and got 0, so you don't have to worry about that. I think the lowest, well, I don't need to tell you what the lowest mark is. The graph will tell you. So let's not get into that. The graph is online. I posted it yesterday. I don't know if you saw it yet. And it has not just the graph of the total, but it's a chart with the distribution per question as well. So you can see for yourself how you did. Good. So that's enough on the midterm. At least it wasn't a disaster. So you can. Well, I'm happy for that. It could have been a lot worse. I've seen a lot worse. I've seen a lot worse. So I'm actually encouraged. Maybe there are a few things that are working here. All right. Second item before we start the lecture, our typical, just a little, maybe 5-10 minutes discussing what should have been the previous assignment. I didn't get a chance to post the editorials, and I'll still try and put in some editorials. Whether I post them in Orville or put them actually on the questions, that's to be determined. But any ones in particular that you want to see or hear about? All of them? Okay, so for balancing act, for example, balancing act, you could done in 1 or 2 ways. You know, you don't actually have to insert any nodes anywhere, right? Because all you have to do, if you know how the tree is going to look when you put it in a heap, you can tell because it's, once you have the number of nodes, it has to be between 2 consecutive complete binary trees. And so you know it's between 2 powers of 2, right? And the power of 2 that it is tells you what the height of the tree is. So the next step, all you have to do is figure out how many nodes are on the left side. And the only thing that will vary there is what's the size of the biggest complete binary tree that is height 1 less, and then add on any extra nodes that you have at the leaf level. So a little bit of arithmetic. You don't actually have to insert any nodes. Now, let's say that you didn't see that. And you wanted to try and actually do some insertions. The hint I gave you was to try some things and see what patterns emerge. You might have noticed that when you look at the numbers going up as you were trying to insert, it kind of looked like a set of powers of 2, but it wasn't quite right. I saw some of you trying to do that. You calculate the height and then you just do something like, right, raise 2 to that and pick the mid value or something a little strange like that. That's only correct when the tree is actually fully complete, when it's a complete binary tree. So what you'd have had to do, you could do that, but for the previous level, and then taking excess nodes at the leaf level into account. So that's another way you could have done that. And some people I saw actually just sort of figure out at what point the number of nodes on the left side exceeded the, how many nodes you need on the left so that the height eventually became the height it must have been. But given the number of nodes, you could calculate what the height was, and so they would just basically pack nodes on the left until the height got to the height it was supposed to be, and you did a little adjustment to check whether you had gone over on the right side or you're still on the left side. Hopsquash Lite, I was actually surprised how come so many people did not get it. So I actually thought I gave you all the code, just not in Python. You didn't see the hints? I posted it on Saturday. You didn't see it? In the RVLE? Well, all right. So I posted pseudocode that basically said, look, it's like exploring, right? So you have the original location for Peter Rabbit. You're exploring from that position. All you need to do is check for three things, 3 steps in that exploration step. One is the current coordinate the location you're looking for? If it is, then you found it, so you return true. If it's not, then you want to check, is the coordinate that you're at already visited? If it is, then you want to exit out of that. In fact, probably you shouldn't even do that. You should just set up a loop. That will be for each next move. And how do you get a next move? Sorry? Well, if you have, what's the name of the thing again? Oh, squat. If you had coordinates RC, and remember that you could take steps A and B, right? In either direction. The next move from there could have been either R plus and minus A, or C plus and minus B. That would give you 4 coordinates. Or you could get R plus and minus B, and then C plus and minus A. That would give you 4 more. And of course, you just throw away the ones outside of the boundary, right? So that would give you 8 possible coordinates of the next position. And then all you want, so build a function to give you that, and throw away the ones that are outside of the grid boundaries. And then inside the explore function, write a loop that would iterate over each of these possible ones, and then recursively explore from there. The only thing you want to make sure you don't do is explore if you've already explored from there, because you don't want to revisit the squares that you've already been to. If you revisit, you'll never terminate, and then you'll run out of time. So how do you make sure you don't revisit? You can, for example, create an array of booleans, right? 1 boolean per grid square. And if you visit it, you just set it true. Initialize down to false. And every time you visit, just set that space to true. And then what you're doing inside the loop is, if any one of these have already been visited, don't explore from there. Otherwise, explore. No? So anyway, go look at the hint that I gave you. I guess I should have marked RC visited. You can do that with a table. You can do that anyhow you want. You could have put that in a dictionary if you want, a hash table. Whatever pleases you. You do that however you want. You check if it's a destination and you know you got there. Otherwise, you would basically just, for each next row, next column in, let's call them the neighbors of row column RC, then you're gonna check if NR, NC not visited, then call explore, return. Explore NR, NC. So that, I mean, I meant to write pseudocode and it's so straightforward, I'm just like belching Python. I'm sorry. I didn't mean to write real code, but it actually is pretty close to done. And that's it. You just have to, I mean, you have to write that, you have to write the code to generate the next move, make sure it's all legal, and you're done. How many marks was that? That would have been 20 points. 25? Wow. All right. What was the other one? Oh, the unique code words. You needed to use a tree for that. No. Ideally, in a theoretical sense, you'd want to use a red-black tree because it's self-balancing and all that. Implementing a red-black tree is a lot of work. You could have gotten away with an ordinary binary search tree. Why? Because more than likely, you wouldn't be getting the elements in a particular order. And that's when the binary search tree is going to be bad. If it's random, chances are the binary search tree is decent. So in other words, you'll have enough branches around so that the depth of the tree won't be too long. The height won't be too large. And so if you had used, so two things. How do you use a tree? What do you put in the tree? You put the code word that you found in the tree, but associate it with a count. So the next time you saw a code word, if you found it already, when you go, so every time you get a new code word, insert it in the tree. If it was already there, then you just increment the count. So now that tells if it's unique, because if the count is greater than 1, then it's not unique. Now, when you're looking for the next code word, what do you want in that case? You just want a successor. So then you just implement tree successor for each key that you're looking for. Okay? So if your tree is good in terms of the height, the cost of finding the successor is only going to be the order of height. If it's roughly balanced, that's going to be like log n. And so you'd have ended up paying log n per code word that you scanned, and at the end, you'd have spent n log n time. Since you only had 10 to the 5th, you have enough time to do n log n operations. Is that kind of making sense some sort of way? All right, good. So, any other questions? All right, so you're gonna kill this week's one, right? If you notice that there's one that's easy this week, yeah, I really owe Janelle an apology for that because she sent me the sketch of the question and I was coding it and trying to build the test cases, and it was originally targeted at medium. And when I was coding it up, I was like, oh, I don't have enough time to finish all this by midnight, and after all this, y'all just going to get 0 on it anyway. So why don't I just why don't I didn't mean that. I didn't mean that. You wouldn't all get 0. A lot of you would. But the point was that you already had one to sink your teeth into, which was the other one. I don't remember it now. So I figured, all right, you have one good one and you have one very easy one. I hope you get it after telling you that. Well, we'll see. By Thursday, if I don't see anything happening, I'll drop 2 hints and see what happens. This time, look for them, please. All right, yes. Who's asking? Who's asking me what? What? What do you mean? Which the problems of the problem of the week? They're always due on Sunday. It's like clockwork. The only thing that disrupts our clockwork is things like midterms, quizzes, you know. But apart from that, it's gonna be every Sunday. Right. All right. Okay, so let's begin the lecture proper. We're actually in a new phase of the course. We are well, not new phase really, new set of topics. This section is all about sorting. And In particular, we're going to be looking at around 6 different sorting algorithms in total. And we're going to kind of progress in increasing order of efficiency. So what in general is the problem of sorting? We kind of take it for granted, but let's just make sure we get this right. What's the problem? What's the sorting problem? It's basically given a set of elements and an ordering relation and we call these elements EI, and then we call ordering relation that funny looking less than or equal to. It's not really less than. Sometimes it's read as precedes. So that's what you're given. What you want to do is return the elements EI in a sequence such that each one precedes the following one. That's not supposed to be so exaggerated. That's a sorting problem. And what we want to do is do this as efficiently as possible. Now we're going to start with the worst possible way. When I say, well, I guess you could make up something worse, but one that's recognized, it has a name, it's used sometimes for very tiny inputs because it's really, really simple to implement, but it's really not efficient at all. As far as we're concerned, it's the whipping boy of sorts. So we're going to compare everything to it, okay? And if you're not doing better than bubble sort, then you're not doing well. It's a funny kind of less than. You can use the word precedes. Whenever you see it, whenever you see it, think precedes. So we're such that E1 precedes E2, precedes E3, precedes E4. Okay? So in other words, if you want, in your mind, mentally, if you think of E1, E2 as numbers, you could think of precedes as being less than, in which case you'd get them in ascending order. But if you were to think of precedes as being greater than, you get elements in descending order. See it? So the idea is, I don't need to talk about ascending order sort or descending order sort. I just talk about sort with respect to some relation. And then that relation determines like what exactly it means. Okay? So in general, this is a general sort problem. For our purposes, we will sometimes revert to the notions of ascending, descending, where we're thinking of this relation as being, for example, less than or equal to specifically or greater than or equal to. But I'll encourage you to think of it in these terms. Okay, so let's look at what the bubble sort does. Well, before I get there though, actually, I should mention this. Why, okay, so you don't get much say in what topics we study in this course. Why do you think, though, that sorting is a whole section of the course? It's going to take up about 2 weeks, no, a week and a half of lectures. What use is sorting? What? I can find them faster. So it enables a binary search. Why do I get that reception? Like, what did I just say? What? You never touched on binary search in first year? Yeah, you should have. If you don't have your elements in order, then it means that searching for your values, well, unless you have them in some other order, in some specific order that doesn't look like a sorted order. Searching for your elements is going to be costly because you won't be guided as to where to look next when you check a particular position. If they're in order, then you can use a binary search. You can check the middle value, and right away, that's supposed to be the median, right? So if you know it's bigger than the median, you've already eliminated half of the possible elements that you were looking for it in. And so if you keep repeating that process, you're at each step eliminating half of the number of possible elements that you would have had to search among, which means that you're going to be running an order login time overall. So in order to reap the benefits of an efficient search, you need to sort sometimes. There are other times when we need to sort, just for the hell of it, because it looks more organized that way, or it helps us find. These papers are in sorted order. I'll beg you to keep them in sorting order by ID, not score, not grade. By ID, so I beg you to keep them in that way when you're rifling through them looking for your paper. Why would I do that? Well, when I was entering those grades, they were already in sorted order on the spreadsheet, so it was easier for me to enter them that way. So even for our own purposes, for our own organization, we might want to keep our data in sorted order. So that's why we sort. But from a computational standpoint, it's very important because it facilitates rapid retrieval, which is through binary search. All right, so now let's look at two algorithms in particular. And if we have time, we may even squeeze in a third. So as I said, beating stick of sorts. It's a bubble sort. How does a bubble sort work? It proceeds in a series of passes. And so you're going to, in a single pass, you're going to repeatedly compare neighboring values. And when they're out of order, meaning that they're violating that precedence operator relation, precedence relation, you're going to swap them. So concretely, think of it as being less than. So when you violate less than or equal to, that means you're looking at greater than. So if the left value is greater than the right value, you exchange them. So what did that just do? That just put them in order. If the left is greater than the right, then that means they're out of order. So swapping them puts them in order. But of course, if you keep repeating this, then that value that you swapped is going to keep getting swapped as long as it comes next to values smaller than it. And it will stop moving once it encounters a value larger than it. By the time you're done, that one pass, the largest value is going to find itself at the very end. That makes sense? And you just run that process again. You keep doing that, starting from the beginning. Each time it moves the largest value that you've not yet finished moving to the end. So by the time you do that, n times roughly, all the elements will be in sorted. If I have to write code for this, how would I? Do I need to write code for it? All right, so there's my precedence operator and there's my array. What am I going to do inside here? I'm going to set up two loops, right? One for the passes and one for the inner pass itself. So let's say that I start from, maybe I should have thought about this before I started writing. Because I think that might need to be off by 1. Okay, how far do I want to go? Well, what the idea here is that I'm going to, inside my loop, compare the jth element with the j plus 1th element. And if they're out of order, I'm going to swap. Okay? But I need this j to go as far as the element before the last one, because I'm going to compare j with j plus 1. So if we're out of order, so we're not respecting the precedence order at the jth element relative to the j plus 1th element, then swap. That's it. I'm out of space. Oh, so useless anyway. No, just kidding. So then swap. All right, let's look at what it would look like on a given set of values. So there's a then swap. This is if true. That should have been lined up. And that was basically it. So let's look at an example. If you have to show bubble sort on the set it will look something like this. So I'll show the first pass in detail, and then I'll just show the result after each pass. And then we can talk a little bit about well, let's first of all, before I get into that, we'll talk about the time complexity of this. And then after that, we will look at we'll look at possible optimizations that we could have done. Okay, so here we go. If I start comparing, so in the first pass, that's just for each pass. This loop here is what's doing all the work in each pass. So I'm going to compare 31 and 15. Use a different color for this. And that causes a swap because that's not in order. Oh, what's the precedence relation I'm using? I'm just going to use less than or equal to. So here we go again. That's going to cause a swap. And now, of course, our index moves up. So now we're comparing these two. 31 and 40. They're not out of order, so no swap here. And so then that's going to compare. So J moves on and compares these two. That is out of order. So then this is going to create a swap here. Tell you what. I'll indicate comparison like so, and I'll indicate swap like that. So that gives us 15, 31, 7, 40, and 3. At this point, the 40 and the 3 get compared, and of course, they get swapped as well. Okay, so do you see why I said the largest value ends up at the end after each pass? Because we're always moving a value if it's out of order. So the largest value, if it's not already at the end, is going to be out of order and it's going to cause a swap with whatever is beside it. That makes sense? So at the end of one pass being when this 4J loop finishes, we would have swapped the largest value all the way to the end. That's why it's called bubble sort, because it's bubbling down to the end of the array. All right, so if you see that, then now I can skip the intermediate. Let me just show you what the array would look like between each of these for loops. After each one, the next time we pass through this, the 31 is going to pass the 7 and the 3, and then stop. It's going to get compared to the 40, but nothing else is going to swap. So then after pass 2, we're going to have 15, oops, no 31, 15, 7, 3, 31, 40. And then after pass 3, we're going to produce 7, 3, 15, 31, 40. And after pass 4, now a couple of things to note. The way this code is written, you notice that we do a comparison because this inner J loop is essentially always running throughout the entire array. It's always scanning these elements. And what that means is that even though we had already moved the 40 to the end, on pass 2, it would have done a comparison between 31 and 40, and then said, oh, they're in order, so don't sort them. And later on, when it finished pass 3, it would have done 15 against 31 and 31 against 40 again, and said, oh, we don't need to move them. So can you think about optimization? Could do what? This here. Yeah, right, okay, good. So the suggestion is that after each inner pass, I could reduce the range that J gets to extend over. Because what am I saving here? I'm recognizing that I've already compared, for 40 to have gotten to the end, I had to have compared 40 with the element beside it. And therefore, if it's sitting there as the largest value, there's no point with continuing to compare the 40 with anything. It's already been done, it's already established as the biggest. No point comparing anything, we could stop before we get to the 40. And likewise, just inductively reasoning, that will be true after each pass. So we could always shorten the range that we run the inner pass to, so that we don't do all these redundant comparisons. Let's talk a little bit about the time complexity and see if it makes a difference. So, how much time does my bubble sort as written take? So let n be the size of the array. You understand what that symbol means? It's the number of elements in that array. Okay? So what's my time complexity looking like? You all have the skills by now, especially after that midterm. Oh, can't see. Can you see now? Yeah, so how do I do my time complexity here? Yeah, whatever. Yeah, swap. Okay, what shall we call? Let's call them swaps. I'm gonna count swaps. You're gonna see why. You see, in sorting is all about moving the data around in the array. So this is one time when we will actually care about how many of those we're gonna do. So the two things we tend to look at when we're considering the cost of a sort is how many times are we looking at elements, how many times do we have to move them, right? So a proxy for examining the elements, I'll just say we're going to count the swaps. That's going to be good enough for us. Obviously, we're looking at elements at least twice in addition to the cost of doing the swap itself. But it's order one plus the cost of the swap, which is essentially order one as well. So for counting swaps, how do you say swaps and memory references? How would I ascertain the total count using this code? You guys, as I said, have the skills. This is a for loop. Okay, so counting swaps, this is in general true. This will be true for all the sorts. Swaps and memory references. All right, so we have T of n is, how do I assess a for loop? It's a sum, right? It's going to be the sum of the cost of the body of the for loop. So it's the sum. Now what's the range of values does I take up? Start from 0 and goes up to, remember the length of array is what we call n. So when we say up to n minus 1, what value does it actually get to? N minus 2. So we start from 0 and it goes up to n minus 2. But that's just how we wrote it. I hope it's right. And then inside what happens? We have another for loop. So that's a sum. This time it's j goes from 0. It also goes to n minus 2. And what's inside of it? Well, there's a comparison. Oh, I'm supposed to count that too. Oops. It swaps, comparisons, memory references. Those are the things that all the sorts are going to need to reference. Sorry? Swaps, comparisons, memory references. Yeah, so what's inside here? Inside this J loop, we have one comparison. We have a swap, possibly, in the worst case. Anything else? If you're really counting memory references, well, you have a constant number, so it's theta 1. But that's not going to change this. So that's our J loop. And that was the end of the body of the I loop as well. So that's the entire cost. You guys all have the skills to resolve that. What is that? Silence. Sum from I equals 0 to n minus 2. If I'm summing j, this is 2. If I'm summing 2 to itself, counting j from 0 to n minus 2, there are n minus 1 copies of 2. And if I'm summing 2 times n minus 1 to itself n minus 1 times, then I'll get, remember at the end of the day, all we care about is the order of growth. So I get an n square algorithm. So bubble sort is an order n square algorithm. Now let's just briefly investigate that optimization that we identified earlier. We talked a little bit about it. We said we could shorten this range. How would that impact my analysis? What would it change? Yeah, I'm gonna do. In fact, a little bit worse, you know. It should improve. It would change this number. So instead of this being n minus 2, it probably would be something like n minus 1 minus I or something like that. Or maybe n minus 2 minus I, given that I starts at 0. So here, I would have had an I in here in the bound, which would mean that this would have become something like n minus 1 minus I, because I would have had that many copies of 2. And now you'd have had an expression involving I inside here, as well as the n. But that's no big deal. You guys have handled this in tutorials and I think on the midterm and all over the place. But at the end of the day, what would happen is you just end up with something that looks like n squared minus half n squared. So at the end of the day, it would still be order n squared. Okay? So even with that tweak, it doesn't change the order growth. It makes it actually faster, about twice as fast, but, I mean, even in the worst case, but doesn't change the order growth. Anything else I could do? Yes? Who's speaking? Somebody just said, sir? Got scared. Is there anything else I could do? I mean, there are a couple other things you can try. So you can tweak your bubble sort to the point, for example, you know, if you noticed, suppose the 3 and the 7 were early in the array. What would have happened is that when you compare them, because you start from the beginning every time, when you compare the 3 and the 7, they would never have moved. So in fact, I don't really have to always start at the beginning. I could start at the last place that I did a swap in the previous pass. Because all the previous, if I've compared and didn't swap, that means they're good. So I don't need to do those comparisons. So even if I do that though, then you'll see that even then, in the worst case, I don't change it, it will still become order n squared. But what will happen is that my best case performance will actually improve. It will improve to order n. All right? So that's bubble sort analyzed completely. Like I said, what we're going to do here is use it as a reference. So I want to keep that in mind. If you're not doing better than bubble sort, you're not saying much. That's how we're going to treat each sort that we look at in detail. I should have asked if there are any questions before I ticked it off. Are there any questions? All right. So we'll talk about insertion sort tomorrow. And probably, I think quick sort is the next one on it. If you want your midterms now, you can come get it. One thing I'll ask you to do when you come and get it is check off on the envelope that you've taken it. When you, in fact, I will check it off when you take it. But I kind of didn't want to be that bottleneck. But I need to know that you collected it if you take it. It's yours. Learn from it. Sorry?